So the consequence of this last equality that tells you that if you've got a linear subspace of a vector space E, then it makes a direct sum with its complement and it creates the whole space E. So few consequences. The first one is that if you have an orthonormal family like this one, then you get that the sum of the scalar product of x with ei square is more than norm of x square. Well, and you've got equality, and equality in case ei en is basis of E, okay? But as long as it's not spanning the whole stuff, then you've got an inequality, which okay, which seems pretty okay. All right. Next thing, we get next corollary. We get Euclidean space E, so finite dimensional linear space with an inner product. We've got subspace F orthogonal. Then of course, because we have this direct sum, we get that F orthogonal is a finite dimensional linear subspace, and because of the direct sum, it's just a direct application of that direct sum ID. The dimensions are coincides, all right? To make E, you need F plus F orthogonal, so the dimensions, and it's a direct sum, so the dimension of F plus the dimension of F orthogonal is equal to the dimension of E, and so you get this equality. And furthermore, you get that also very intuitively, the orthogonal of the orthogonal is going to be the vector space you started with. That's also pretty intuitive. Let's just take a few seconds to prove that. Okay. Right. So how should we do? Okay, the first thing that we can easily prove is that the orthogonal of the orthogonal is going to be included in F, okay? How can we prove that? So let's take X that belongs to F orthogonal, and then what do we get? And Y that belongs to the orthogonal of the orthogonal. Okay, so by definition, what does it mean? It means that X and Y are equal to 0 because Y belongs to the orthogonal of the space that F belongs to. Okay, so what does that mean? It means that for any X that belongs to F orthogonal and any Y that belongs to the other space, it's equal to 0. So that means that Y belongs to F also. Okay. All right. So we have this thing, and also we have that from the dimension consideration that's just above, we get that the dimension of the F orthogonal is equal to the dimension of E minus the dimension of F orthogonal. Okay, but by definition, by the previous stuff, of course, we have that this also is equal to the dimension of F. Okay, so this space F orthogonal is a subspace of F, and they have the same dimension. So the only subspace of a finite linear subspace of finite dimensional space that have the same dimension of the space itself is itself. So we get that F is equal to the orthogonal of the orthogonal. Okay, which seems pretty intuitive. All this, actually, this orthogonality ID will make things work exactly how we feel it should work. Okay, before we have, knowing about, well, before introducing this way to measure orthogonality. We could go in any direction, and well, we could have we could have relative directions that wouldn't really be orthogonal or collinear or whatever. It would be anything. So we had many possibilities, and sometimes the intuition would not follow. Whereas here, it's going to be very, very direct. Okay, it works as we expect it to work. Okay, so. And that's, by the way, that's why it's called the Euclidean space. It's called the Euclidean space because it works as the usual geometry in R2 and R3 that we can define. Then we can define any finite dimensional space. It may have 10,000 dimensions, as long as you have a nice inner product that is defined on it. It's going to behave in the same way as things behave in the plane or in space. Okay, so it's called Euclidean space, and it makes things very nice to work with. Okay, so that leads us to orthogonal projection and distance. Okay, all right. Okay, so first the definition of the orthogonal projection. So we are in a vector space E, and we have a finite dimensional subspace F, and we know it makes a direct sum with its orthogonal complement to create E, and so we can define, as we expected, the orthogonal projection to be the projection on F along its orthogonal. Okay, so previously we needed a space and we needed any direction. Okay, and we could take the projection on, let's say that was F and G. We could take the projection on F along G. Now we're going to change that into an orthogonal. The space G is actually going to be now the orthogonal complement of the space F. Okay, so F orthogonal, and so that F, when we have that, for instance, if we start with the same X, we will take its orthogonal projection, okay, and we still have the same decomposition into one item that belongs to F and one item that belongs to that's F and one item that belongs to its orthogonal. Okay, well, to the other space. All right, so that's going to be the orthogonal projection, and again, it's actually going to be a bit simpler than before because it's really what we would like to do. Instead of taking any strange direction to project along, we'll just take the straight one. Okay, so next theorem, denote P the orthogonal projection on F. Then if X belongs to E, P of X, so the projection on F of any X in E, is fully characterized by saying that, well, we get P of X that belongs to F and X minus P belongs to F orthogonal. Okay, so again, same stuff. So now we've got the orthogonal projection. Okay, and so we got one part at XF, and XF orthogonal is actually given by X minus X XF. What changes here in contrast with the idea of projections that we had before is that this is uniquely defined just simply because any X that belongs to E can be described uniquely as one XF and one XF orthogonal, and this is, as this is a direct sum, this is unique. Whereas when we had this and we were saying that, well, we take one X1 that belongs to F and one X2 that belonged to G, actually, well, we could find um, this wasn't, they were not, they would not belong to orthogonal spaces to each other. Okay, so you remember, it's like when we are building some vectors out of non-orthogonal vectors using the Gram-Schmidt. In order to build the orthogonal vector, we consider the vector we have and we subtract its component along that direction. Okay, so it's more or less the same kind of idea. We don't have any redundant information here. Okay, in whereas here we sort of had some reason. Well, it was not going to be the most direct way to go from my point to my plane F. Right here, I've really got this unique decomposition. Okay, whereas before when I had a non orthogonal projection, I could have many directions that would give me this projection, okay? And so I wouldn't have a unique way to define the direction of the projection. All right. Anyway, now it's going to work much better. And so again, that second part to say that given an orthonormal basis of f, then the projection is going to be well, it's just very naturally given by this. It's really linked to what we showed before. Okay, this is something we showed in a previous proof that if px is the xf component, so it's the xf component, we know it's going to be the sum of xf ei, but we could show times ei, but we could show that this was really the same thing that's from the proof of previous proposition, that's these components, they are also given by the scalar product of x with the ei themselves. Okay, so n equals 1 to n, I equals 1 to n. Okay, and next comes definition. The distance between an item, an element, and a linear subspace is going to be defined as the smallest distance between x and any element of the subspaces, and maybe you already see that coming. It's going to be defined as, well, we're going to get that it's going to be given by the orthogonal projection of that element on the linear subspace. Okay, so that's going to be the next video.